Picture this. You wake up tomorrow morning, turn on the tap, and nothing comes out. Not because of a broken pipe. Not because you forgot to pay a bill. But because the plant that makes your water, the one pulling it from the ocean and turning it into something drinkable, got hit last night. Now ask yourself, how long could your city survive? For most people watching this in the West, that's almost a philosophical question. You've got rivers, lakes, rainfall. You've got options. But there are nations on this planet where that question has a very specific, very terrifying answer. 10 days, not 10 months, not 10 weeks, 10 days. And right now, in 2026, that clock isn't hypothetical anymore. It's ticking. Section I. The Achilles heel nobody's talking about. Let me give you a number that should stop you cold. 6%. That's the share of the world's population living in the Middle East and North Africa. Now here's the other number, less than 2%. That's their share of the world's renewable freshwater. Let that mismatch sink in for a second. Hundreds of millions of people. Almost no natural water. And they've been solving that problem by doing something that sounds like science fiction, but is now as routine as turning on a faucet. They're mining the ocean. The Middle East runs the largest, most concentrated network of desalination infrastructure on the planet. Saudi Arabia, the UAE, Kuwait, Qatar, Bahrain. These countries don't just use desalination. They are, functionally, dependent on it for survival. Qatar, 99% of its drinking water comes from the sea. Kuwait, 90%. Oman, 86%. These aren't marginal figures. These are civilizational dependencies. And since early 2026, with conflict escalating across the region, strikes on plants in Qeshm Island, Brine, Kuwait, the world's most extreme water infrastructure has become the world's most extreme military target. Most YouTube channels covering the Middle East are showing you Neom's flashy architecture or drone footage of luxury resorts. We're going to show you something far more important, the invisible engineering keeping hundreds of millions of people alive, and exactly how fragile it really is. Section I, the brutal math of hold water. Here's something most people don't understand about the Gulf states. They didn't always depend on the ocean. For thousands of years, communities across the Arabian Peninsula survived on groundwater. Ancient aquifers, slow, moving reservoirs built up over millennia. The kind of water that doesn't require a massive industrial process to drink. That water is gone, not running low, not being carefully managed, effectively exhausted. The shallow groundwater that was the region's only truly renewable source has been pumped down to the point where, in most Gulf states, it's no longer a viable option at any meaningful scale. So, what happened? Population exploded. Cities grew at speeds that have no historical parallel. Riyadh went from around 150,000 people in 1960 to over 7 million today. Dubai didn't really exist in any modern sense 50 years ago. These are cities that were built faster than nature could provide for them, and desalination filled the gap. Between 2020 and 2025 alone, GCC states poured over 100 billion into expanding desalination capacity. That's not foreign aid, not international development money. That's state-driven industrial investment, treating water security the same way other countries treat defense spending. Because for them, it is defense spending. But here's the part the investment numbers don't tell you. Even with all that capacity, the reserve buffers are terrifyingly thin. Official figures from Qatar suggest 4 months of water reserves. Dig into the actual municipal supply chains, factor in realistic consumption rates and distribution constraints, and independent analysts put the functional survival window much lower, somewhere between 7 and 10 days in a complete shutdown scenario. Kuwait 10 to 15 days. UAE, with extreme rationing, maybe 45. These aren't apocalyptic projections from doomsday blogs. These are engineering realities. Desalination plants run in real time. They don't stockpile water the way you'd stockpile grain. And that means every single day, the ocean has to keep cooperating. Section IE. The problem nobody wants to talk about, okay? So desalination works. It's keeping hundreds of millions of people alive. It's proven technology. You pump seawater in, you push it through membranes under enormous pressure. We're talking 60 to 120 bar, roughly 50 to 100 times the pressure in a car tire. And clean water comes out the other side. What comes out the other side of that? What's left over? Brine, hyper, concentrated salt water, roughly twice as salty as the intake, pumped back into the sea. And here's where the story gets darker in a way that almost nobody in mainstream coverage bothers to explain. The Red Sea is not the Pacific Ocean. It's not a vast, open body of water with unlimited capacity to absorb and disperse what you dump into it. It's a semi-enclosed basin, long, narrow, with limited circulation. The brine that gets pumped back in doesn't just go away. It sinks, it concentrates, it accumulates. But the chemical problem runs deeper than salt. Modern desalination discharge isn't just brine. The pretreatment process uses sodium hypochlorite, bleach, essentially, to kill biological material that would clog the membranes. It uses ferric chloride as a coagulant, sulfuric acid to control pH. That chemical cocktail goes back into the water along with the salt. The result: coral bleaching events that correlate directly with plant discharge zones. Disruption of the marine food chain in areas that millions of people still depend on for protein. And this is the part that creates a genuinely vicious cycle. Intake water for the plants themselves is getting progressively saltier and harder to process as the brine concentration in coastal waters rises. More brine means more energy needed to push it through the membrane. More energy means higher costs. Higher costs mean either you pay more or you cut corners. And in a system where the margin between functioning and crisis is already 10 days, cutting corners isn't really an option. There's also a strategic vulnerability that military planners lose sleep over. Many of these desalination plants are co-located with power generation facilities. Specifically, they're designed to capture waste heat from power plants to improve efficiency. Economically brilliant, militarily catastrophic. One strike takes out both water and electricity simultaneously. That's the world these countries are operating in. Section IV. Wait, what if the waste is the treasure? Now I want to flip everything I just told you. Because here's where the story gets genuinely extraordinary. That brine. That chemical cocktail that's been treated as a pollution problem for 50 years is starting to look less like waste and more like an untapped mine. Think about what brine actually is at the molecular level. It's not just sodium chloride. Seawater contains trace amounts of dozens of elements: magnesium, potassium, calcium, bromine. And in the hyper-concentrated brine coming out of desalination plants, those trace elements are suddenly concentrated enough to be economically interesting. Most interesting of all, lithium. The same lithium that goes into every EV battery, every AI data center power supply, every smartphone you've ever owned. Global demand for lithium has exploded as the clean energy transition accelerates and traditional mining operations, tearing up hillsides in Chile, extracting from underground brines in Argentina, are struggling to keep up. New extraction technology, now being piloted at scale in the Gulf, can handle brine with salinity exceeding 150 xylosin parts per million, far above what older systems could process, and pull lithium out with enough efficiency to make the economics work. Global lithium production from brine sources has jumped 25%. And if Gulf desalination plants can be retrofitted to function as mineral extraction facilities simultaneously, the entire economic calculus of desalination changes overnight. You're no longer just paying to make water. You're mining critical minerals as a byproduct. The industry term for the end goal of this approach is Zero Liquid Discharge, ZLD. The concept is exactly what it sounds like. Nothing goes back into the ocean. The water gets recovered and reused. The salt and minerals get concentrated into solid, sellable material. Roughly 70% of new industrial treatment facilities being built right now are integrating ZLD-based systems. Recovery rates for water in these systems are hitting 98%. This is the reframe that changes everything. The Gulf states aren't just trying to solve a water crisis. They're potentially positioning themselves to own a critical piece of the global technology supply chain. The minerals that power the world's AI and electric vehicle infrastructure. Extracted from the same ocean they've been fighting over for decades. Section V. The technology that could change everything. Let's talk about where the engineering is actually headed. Because the current state of the art, reverse osmosis membranes at 2.9 to 3.33 kilowatt hours per cubic meter high pressure, significant infrastructure, is already remarkable. But it's not the ceiling. At King Abdullah University of Science and Technology, KAUST, on the Red Sea coast of Saudi Arabia, researchers are in pilot-scale testing of a polymer membrane that operates on a fundamentally different principle. Instead of the relatively large pores of current RO membranes, this material uses sub-nanometer-sized pores. We're talking about gaps smaller than a single nanometer, smaller than most molecules, operating with a precision that's almost biological in nature. The result, 40 liters of fresh water produced per hour per membrane unit, at room temperature, consuming just 1.88 kilowatt hours per 1,000 liters. Compare that to the 2.9 to 3.33 kilowatt hours of standard reverse osmosis, and you're looking at a potential 40% reduction in energy consumption. At the scale the Gulf operates, billions of liters per day, that's not a marginal improvement, that's a transformation. Meanwhile, advanced graphene oxide membranes in late-stage development are hitting salt rejection rates of 99.7%, meaning out of every 1,000 salt molecules trying to get through, only 3 make it, while operating at pressures 30% lower than current systems. And then there's the integration angle that almost nobody is discussing yet. In 2026, the conversation about AI data centers and energy consumption is everywhere. These facilities generate enormous amounts of heat. Coastal data centers, and there are increasing numbers of them being planned or built along Gulf coastlines, need cooling systems. Desalination plants running reverse osmosis also need energy and generate heat. The emerging model pairs these systems together. AI manages the desalination process in real time, optimizing membrane pressure, predicting maintenance needs, modeling the incoming water's salinity hour by hour. The data center's cooling loop integrates with the water treatment cycle. Wave energy systems, with AI modeling ocean patterns in real time to optimize turbine positioning, power the whole thing. It sounds futuristic, but the components are all real, all being tested, all moving toward deployment. Section V, the bigger picture. Here's where I want to leave you. The story of Middle East desalination isn't just a story about water. It never really was. It's a story about what happens when a civilization outpaces its natural environment and then has to invent its way out of the consequences. The Gulf states have done something genuinely unprecedented in human history. They've taken one of the most water-scarce regions on Earth and built modern cities of millions, sustained entirely by industrial chemistry and ocean engineering. The scale of what they've built is staggering. The vulnerability underneath it is equally staggering. But the trajectory of the technology suggests something that the doom and gloom coverage tends to miss. These countries are not just defending a fragile system. They're actively trying to transcend it. If the brine problem gets solved through mineral recovery, if ZLD becomes standard, if lithium extraction from desalination byproduct scales commercially, then the Gulf doesn't just solve its water crisis. It potentially becomes the world's most important supplier of battery-grade lithium, extracted at effectively zero additional environmental cost from infrastructure that's already running. If the membrane technology at KAUST scales from pilot to commercial, if energy costs drop by 40%, then desalination becomes viable in parts of the world where it currently isn't even on the table. Sub-Saharan Africa, South Asia, communities right now that are watching their groundwater disappear with no engineering solution in sight. The Middle East built civilization in a desert. They're now building the technology that could sustain civilization everywhere. The 10-day clock is real. The vulnerability is real. The conflict over this infrastructure is real and escalating. But so is the engineering response. And the researchers and engineers working on this problem understand the stakes in a way that very few people elsewhere do. Because for them, this isn't an academic exercise, it's survival. And historically, survival has always been the most powerful driver of human innovation. If you made it this far, thank you. This is genuinely one of the most important infrastructure stories of our time, and almost nobody is covering it with the depth it deserves. Drop a comment below. Which part of this surprised you most? The 10-day reserve window, the lithium angle, the membrane technology? I read every single one. And if you want to understand the other invisible systems holding the modern world together, the infrastructure nobody talks about until it breaks, subscribe, because that's exactly what this channel is about.